Hello ladies and gentlemen, and welcome to a new Hazeltest video. Today we are going to take a look at the map load runner batch test loop combination. Let's go. This is part 2 in the Let There Be Load series. Last time, that is in part 1, we introduced the map load runner, the batch test loop and the boundary test loop in more theoretical terms, and today we're going to take a look at the map load runner batch test loop combination in practical terms. So, what's on the agenda for today? As always, we're going to kick things off with a short recap, then do a little bit of setup work for our live demo, then head on to said live demo, and finally do a short summary and perform what I called an outlook. When I say outlook, I do not mean, of course, everyone's, let's say, favorite turn-based strategy game, aka dreadful email program, aka Microsoft Outlook. No, I mean a short outlook into the future of what you can expect next in terms of videos on this channel. Right, so let's start with our recap. And the first topic for our recap is the load dimensions. Those load dimensions, they keep reappearing, don't they? Yes, that's because those load dimensions is the framework within which we can measure load, both in terms of the Hazelcast cluster, that is both from the perspective of the target Hazelcast cluster and from the perspective of Hazeltest, that is the actor that creates that load. And previously, in the previous video that is, we introduced 6 load dimensions in total. The number of items, the item size, the number of data structures, the number of clients, fifth, the cluster health, which we define as a kind of meta dimension, and finally, sixth, the operations per second. Now, there is a feature available in Hazeltest that lets you influence load dimension 5 as well. It's called the Chaos Monkey, and it does pretty much exactly what it sounds like. But the Chaos Monkey is not the star of today's video. So today we're going to use all the load dimensions except load dimension number 5 in order to configure our Hazeltest instance or instances. Next up is the relationship between runner and test loop. As of today's video, there are 2 map runners available in Hazeltest, the Pokédex runner and the load runner. And there are 2 test loop types available too, the batch test loop and the boundary test loop, which begs the question, how do they relate to each other? Because even if you haven't watched any of the previous Hazeltest videos, looking at the slides you've seen thus far alone would imply that runners and test loops are distinct yet somehow related concepts in Hazeltest, right? So how do they relate to each other? Well, a runner can be configured to use exactly one type of test loop. You can therefore think of the runner as the kind of parent element, whereas the test loop would be the child element. So, which component does what? Well, as a rule of thumb, the runner offers adjustability for load dimensions, but it's not the actor that executes operations on a target Hazelcast cluster itself. Instead, that's the job of the test loop. So it's the test loop that controls the execution of operations on the target Hazelcast cluster. And the exception to that rules is sleeps. This corresponds to load dimension 6 because the less you sleep, the more operations per second you can execute, right? So that's load dimension number 6. And sleeps are also, sleep configuration that is also offered by the test loops. Short example of this, the map load runner lets you define, among others, the size of each map item as well as the number of items, which correspond to load dimension 2 and load dimension 3 respectively, but it's the test loop that determines the frequency and the order of operations on the cluster. In order to drive home this point, I brought a couple of screenshots with me. On the left-hand side, you can see the map load runner batch test loop combination, which is exactly the combination we are using today. And on the right-hand side, you can see the map load runner boundary test loop combination. To make those screenshots, the configuration for the map load runner was exactly the same. The only thing that's changed was the type of test loop. Therefore, depending on the test loop you choose, the sort of load patterns, let's say, you will observe on your target Hazelcast cluster on the test will be totally different. Speaking of the batch test loop, let's do a very short recap of what that actually is. The batch test loop is called that because it executes operation batches. In fact, it executes an ingest all batch, and then a read all batch, and then a delete sum batch, where the sum element is subject to a certain randomness, and then rinses and repeats basically. So it literally just executes operation batches. That's how simple it is. If you look at the code, you wouldn't believe how simple the actual implementation is. So the problem with this is that regardless of the invoking runner, that kind of load, or the kind of load that gets generated by this kind of executions, is simply not very realistic, right? But here's the thing. In the early development of your release candidate, that is in the early phases of assembling, let's say, a new Helm chart that describes your target Hazelcast cluster, the degree of realism for that load generation is actually far less important than minimizing the time it takes to get feedback on the fitness of that release candidate. Therefore, it's a good idea to run a short smoke test in the CI/CD pipeline that assembles and deploys your release candidate. A smoke test could, for example, be that you expose the resulting Hazelcast cluster, that is, the Hazelcast cluster that is a result of, for example, applying your Helm chart to a Kubernetes cluster, to as much load as possible within the shortest possible time, if that's the sort of statement about the release candidate fitness that you want. Either way, it's a good idea to do that as quickly as possible in order to minimize the time it takes for you to get that feedback. And that is to maximize the number of iterations you can do on the release candidate within one given unit of time. As it turns out, the combination of the runner framework itself, which is basically just Hazeltest because it's the sort of engine that runs all the runners, plus the mapload runner, plus the batch test loop, is a great fit for that. Load dimensions 1 through 4 are adjustable through the mapload runner plus the runner framework, which again is Hazeltest surrounding the runners. Then load dimension 5 is out of the question for this one because that's subject to the Chaos Monkey, right? The only load dimension that's left really is load dimension 6. In order to get quick feedback, you'll want to execute operations on the target Hazelcast cluster quickly. So you want the operations per second to be as high as possible. So in order to optimize for that, you need a fast and lightweight test loop. And as it turns out, the batch test loop, due to its simplicity, is very fast and lightweight, and as an added bonus, it's also very, very easy to configure as a result of its simplicity. We are going to find out how easy the batch test loop can be configured and just how fast and lightweight it is in scope of the live demo. But before we can go to the live demo, we need to do a little bit of setup work. We need to establish an example use case that we can use as the platform for everything that sort of unfolds, and derive a challenge from that example use case that sort of naturally presents itself, and then in turn derive the test goals from the challenge, because the test goals also, of course, kind of naturally, present themselves when looking at the challenge. So let's start with our example use case. As always, our assumption is that we deploy Hazelcast to Kubernetes. Therefore, our dummy release candidate, or our presumed release candidate, let's say, as always, is a Helm chart. Also, we're going to assume that there is a CI/CD pipeline in place to build the release candidate and deploy it to the target Kubernetes cluster. Now, I didn't actually build or provide a CI/CD pipeline for this live demo, but that's not the point of this video, really. The point of this video is to simply show you the next point, which is to expose the Hazelcast cluster to to run a kind of sanity check on the Hazelcast cluster, right? So sanity checks are important in order to sort of verify a very basic level of fitness on our release candidates. Now, what's a sanity check? Well, if you work in IT support, for example, and I don't know, Karen from controlling calls you saying, "My screen doesn't work," then the sanity check would be to ask her whether it's plugged in. That's a sanity check. So for the purposes of this live demo, Let's just say generally that a sanity check is something that is very easy to verify, but can have catastrophic consequences when it's left unverified on your release candidate. Another sort of more realistic example, perhaps concerning Hazelcast itself, would be the configuration of the van queue size. Let's say you want to retain 100,000 elements on your van replication queue in case the target Hazelcast cluster goes down and your queue, keeps filling up. So configuring 100,000 elements is terrific, except it will really hurt you if the JVM's heap is too small to actually accommodate all those 100,000 elements, right? If that happens, then the JVM of your Hazelcast members will run into out-of-memory errors, and if that happens in production, it's really just, a pain in the bottom, because, well, crashing Hazelcast members in production is just something that should never happen, right? So, and it can be so easily avoided, by means of simply testing, well, what happens if my target Hazelcast cluster for the van replication goes down, and what happens if the van replication queue thus fills up? Is my heap large enough to do that? You can do, of course, the calculation on paper, is the heap large enough to accommodate all those elements? But it's probably a good idea to run a test just for good measure, right? So that's not a sanity check we're picking as an example, however. The sanity check we're going to pick is the assertion that a combination of memory parameters is safe for the Hazelcast members, even when they are on the maximum memory capacity. And that's a great use case for the batch test loop map load runner combination, because we can actually optimize for ingesting data as quickly as possible. There are 3 memory configurations we have to get right. 2 of them are on Hazelcast side, 1 of them is on Kubernetes side. The first one is the native memory size. Native memory is an enterprise-only feature, but we're actually going to use an enterprise version, or the enterprise version of Hazelcast. Thank you, Hazelcast, for providing me with an enterprise license so I can do this live demo in the way I wanted it to do, which is that, we're using native memory. So that's awesome. Thank you. And the other configuration parameter on Hazelcast side is the aforementioned max heap size that we need to get right as well, of course. And then the third configuration parameter is on Kubernetes' side. It's the memory limit on the container within the Hazelcast pod. Now, obviously, there is the min heap size as well that, strictly speaking, we need to configure, but it's best practice for Hazelcast to set min equals max heap anyway, so, we just won't bother with the min heap and set that to equal to the max heap instead. And also, obviously, there is a memory request that we need to specify on the Hazelcast container within the pod as well. But again, it's best practice for the pod to get the highest quality of service class guaranteed in Kubernetes to simply specify request equals limit. So similarly, we won't bother that much with the request and simply set it equal to the limit. So at the end of the day, we end up with 3 configuration parameters that we really need to look at. This is a simple yet interesting example because Kubernetes enforces the memory limit on the level of each container within a pod and, importantly, kills all the containers that violate their limit. And therefore, setting the container memory limit equal to the sum of the native memory size and the JVM's max heap size is a really bad idea generally, because the JVM requires some additional memory on top of what's stored on the heap, right? Therefore, it's necessary to leave a little bit of buffer, a little bit of wiggle room, let's say. But on the other hand, you don't want the buffer to be too large, because the buffer that's too large will mean that, a lot of memory and therefore a lot of money at the end of the day will go to waste, right? So for example, if the container memory limit is 20 gigabytes and the sum of native memory plus max heap size is, 12 gigabytes, then that's a really safe memory configuration. But it will also make sure that a lot of memory and therefore a lot of money goes to waste. So that's not ideal either, right? So what we need, therefore, is a smoke test that brings our target Hazelcast cluster to its maximum memory capacity as quickly as possible, so we can iterate over our memory configuration as quickly as possible. And that means that our CI/CD pipeline is supposed to build and deploy the Helm chart, automatically run the smoke test, and then repeat if we find a flaw in our configuration. If you have an estimation for the payload size that your Hazelcast clusters are likely going to face in production on one hand, and on the other, know the total amount of memory to exhaust in your target Hazelcast cluster, that is not the target Hazelcast cluster in production, but the one that is spawned by your release candidate, then the goal at first is to optimize along load dimensions 1, 3, and 6. That is, the number of items, the number of data structures, and the operations per second. These load dimensions define what a single Hazeltest instance can do in terms of, filling up memory as quickly as possible without deviating from that payload size estimation, which would be load dimension 2. If that is insufficient to create, load quickly enough so the smoke test is reasonably short, then at first we'll try to scale out horizontally, that is, adjust load dimension number 4, the number of clients. And if even that is insufficient to fill the memory quickly enough, then we'll have to deviate from that payload size estimation and also optimize along load dimension 2. So let's see what the live demo has in store for us. And as always, we're going to switch to the IDE/terminal in order to do that. Before we jump into the live demo, I would like you to meet someone, or something rather. The big fat old server, aka energy to heat converter, that sits below my desk. It's made itself known in the, shall we say, audio atmosphere, and I'll give you a couple of seconds in order to fully indulge in it and appreciate it. Here we go. Yeah, that's the noise I'm talking about, and as far as your ears are concerned, I should probably call it energy to noise converter. Yeah, that's the big fat server that we're going to use in today's live demo. And unfortunately, yeah, I know, you might ask yourself the question, why is it in your room and why didn't you put it outside of your room? That's a very good question, thank you very much. Well, it's just that if I put it outside my room, the noise would annoy my girlfriend greatly. And our flat simply does not provide for a room in which, I could put it and, none of us could hear it. And so yeah, it has to sit below my desk, unfortunately. Why didn't you use an AI filter to remove the noise? Also a very good question, thank you very much. Well, the AI companies won't like to tell you this, and they won't like to hear it. But AI filters, or AI-based noise removal tools, have their limits. Trust me, I tried running this live demo with an AI filter running in the background, and it just completely butchered the noise. So the outcome was, like me talking from the inside of a tin can or something. So it was completely impossible to listen to. So this is a lot better than whatever result the AI filter tool came up with. I tried to soundproof it a little. I put some pyramid foam around it and some fabric on it and something. But unfortunately, it's still on the audio track, and I hope it won't bother you too much. So before we do anything, let's walk you real quick through all the stuff that we need, in case you feel inclined to swim along in this live demo. So let's go from right to left. On the right-hand side in the desktop layout, I got two repositories open in the browser, Hazeltest and block-examples. Hazeltest is what I recommend you clone, not necessarily due to the source code, although that's something you can, of course, dive into if you feel so inclined, but due to the resources/charts directory. In here, there's not only a Hazelcast chart and a Hazeltest chart, obviously, but also Prometheus and Grafana, both of which come in very, very handy if you want to, not only deploy Hazelcast and provide some load for it, but also monitor what's going on your cluster, right? So that's something I recommend you clone. And the block-examples repository is well, what we're going to use today, because there are YAML files in there that will come in most useful. The folder that you're gonna want to check out is how to Hazeltest the map load runner. And today we're using the batch test loop, so that's what we're looking for. Unsurprisingly, there are subfolders for Hazelcast and Hazeltest, and I'm just gonna switch to the IDE in order to show you how this live demo will play out. So we got 3 stages in total for our Hazelcast configuration, and these stages mark the iterations that we will do on our quote-unquote release candidate. So the Hazelcast Helm chart in combination with the configuration stored in these files could be seen as our release candidate. And I'm going to walk you through these files in just a second. And then we've got Hazeltest files for in total 2 relating to 1 stage each. So as you will notice, there we stop at stage 3 in Hazelcast, but there is no stage 3 configuration, load configuration file for Hazeltest. That is simply because we will consider values stage 3, that is the configuration stored in here, to be our final iteration. Of course, we could easily come up with a Hazeltest configuration that makes even the stage 3 Hazelcast clusters fail and crash, or the members fail and crash rather, and then, you know, come up with stage 4 and then create yet more load and come up with stage 5 and repeat that ad infinitum or until our coffee machine breaks or we run out of coffee. But in the interest of keeping this live demo reasonably short, we'll just call it a day at the end of stage 3. So, one desktop to the left is the aforementioned Hazeltest repository, and I'm just gonna install our stuff from within here. And then, of course, we've got our terminal. There's not much going on there currently, but we're about to change that. And as always in these live demos, I use K9s in case you work with Kubernetes or OpenShift or any other flavor of Kubernetes that is out there. Make sure to check out K9s. I am in no way affiliated with K9s. I just think it's a really, really awesome tool for managing, you know, Kubernetes or looking at and interacting with Kubernetes and OpenShift workloads. So let's get ourselves some pods deployed. And we're going to start with Hazelcast because Prometheus and Grafana have already been installed. So these 2 components are ready to go. All we need next, therefore, is a Hazelcast cluster and, of course, Hazeltest to give it something to think about. Gonna install it. No, actually, I'm gonna type everything out here so you can, you know, replicate this in your local setup if you so desire. Hazelcast with man center -n Hazelcast platform, and you can see here in the background that I'm using the Hazelcast Enterprise version, and I enabled usage of that Enterprise version with this little switch here. And if you want to do the same, that is, if you have requested a Hazelcast Enterprise license, just make sure that you have a secret in your Kubernetes or OpenShift cluster with this particular name. Could be any name in your case, obviously, just make sure it's the correct name in your case. And there's also, you know, the key path to configure. So please make sure that is correct, or else your Hazelcast cluster won't be able to read that enterprise license and it will refuse to start. So -n Hazelcast platform, and then of course we need a file. And for that, I'm gonna go for an install of simply the raw version of the values stage 1 YAML file. Right, and off we go. So these pods are getting installed. This will take a couple of seconds, and while they are getting pulled up, let me show you this configuration file, because the configuration error here is rather easy to spot. Let's say our predecessor, let's call him Dave. Let's say Dave was tasked with the introduction of native memory. So let's say your company used Hazelcast Community and then switched to Hazelcast Enterprise in order to be able to use native memory storage. So Dave was tasked to introduce native memory, and he's done a so-so job with that. So he's successfully enabled native memory. Congratulations. And he has successfully provided a native memory size. However, he forgot to adjust the maximum heap size and obviously the minimum heap size corresponding to that as well. So now 16 plus 16 is far more than our limit of 20 GBs that we have configured on the Hazelcast container within the pod. The dangerous thing about this configuration is that it will work as long as there isn't a lot of load on the Hazelcast cluster or on those Hazelcast members that have been started with this configuration. So that's precisely kind of the sanity check scenario that we're looking for, and that we should definitely, that's the kind of sanity check that you should definitely run before letting this configuration anywhere near your production environment. So in the meantime, all the pods have come up. Let's check the logs. Yeah, there is an exception in here, some error message, but that doesn't bother us right now. The Hazelcast license, yeah, it's a trial license. Mine will expire in 19 days, but other than that, it all looks pretty good. So let's take a look at the browser, in fact. Go over here to the Hazelcast Management Center and also open up Grafana at the same time. So here we are, Hazelcast Management Center. We can see there's nothing going on in our cluster, and then, of course, here's our special dashboards. In case you follow me on LinkedIn, you might have seen a post introducing those dashboards that I built for this live demo, and today we are going to use precisely those dashboards. No surprises. So that's what, as you can see, I've done a couple of iterations on this live demo already in order to make, the recording as smooth as possible. So there's a couple of data points there, but yeah, everything's up and running now. So that's the memory we have to fill, about 48 GBs in total. That's what we have to fill. 46.9. It's not actually that much because the net storage we can use in this target Hazelcast cluster is a little bit less than that due to the eviction policy defined on the map, which will evict map entries at what did I configure? I think 80% of used memory. Wait, let me check this out. So platform config map ht underscore, and then there is the eviction policy. Yes, exactly. So free native memory percentage 15. So that's another way of saying once 85% of the native memory on the members are exhausted, eviction will kick in. All right. Plus we need to configure the metadata space percentage that we have configured for the Hazelcast cluster, or for the Hazelcast cluster members rather. So the actual net memory that we're gonna have to exhaust to bring those clusters to their memory capacity in terms of the native memory is somewhere between 41 and 42 gigabytes, 41.6 roughly. So our Hazelcast cluster is running with the stage 1 configuration. So let's see what happens when we deploy our values stage 1.1 Hazeltest configuration. Let's walk you through it real quick. One replica only. Our goal here is we're still aiming for those 48 GBs in total. In total, like if you look at this configuration, you'd think that this would give you 3 into 16 gigabytes, right? So naively, you could simply say, well, that's 48 gigabytes of memory to exhaust. And we're still aiming for that. Because remember, we want to go over a little bit. We don't just want to reach the maximum amount of memory that the Hazelcast cluster is able to store. We want to go over in order to make, or in order to assert that the configuration is stable enough, even if clients continue to write to those members, even if the memory has already been fully exhausted. So we've got 30 maps in total, and if you do the numbers, that simply means that we need 400,000 number of entries per maps with a given item size of 2 kilobytes. So that's an easy enough configuration, and of course, because today we take a look at the map load runner batch test loop configuration, the test loop configured is the batch test loop. Also, we've already optimized for load dimension 6 because the sleeps that the batch test loop offers have both been disabled. This is basically like saying, give it all you've got. So we let that batch test loop run as quickly as it possibly can, and the only limit is really the CPU limit on the Hazeltest pod itself. So let's deploy this. And let me just bring up the correct file. It's this one. And we need the raw file for that. You may notice that I'm using 0.16.3-dev7 of Hazeltest. That's because I'm currently working on a bug fix that simply reduces the memory footprint a lot. But this dev7 version is safe to use. It's the 8th iteration I'm doing on this release candidate, and the only reason it hasn't been merged yet into 0.16.3 is the fact that I'm still not quite happy with the test automation, so I want to implement some more tests and then merge it. But in terms of actual functionality, this is done and therefore it's safe to use. But by the time you're watching this video, it's likely that 0.16.3 is actually out and you'll be able to do this live demo on the 0.16.3 version. Either way, we are just gonna install Hazeltest like this. Helm upgrade -- install Hazeltest. Hazelcast platform -f this particular file. All right, let's go. And it's already running. That's great. So let's head on over to our management center. There is now 30 non-system internal maps. That is 30 payload maps. Great. And yeah, let's miss that alert. And let's see what our dashboards say. In particular, I want to see what the maps dashboard does. What we expect, of course, is some movement within those lines. So remember that our goal is to completely exhaust the memory of the target Hazelcast cluster in a time as short as possible, right? In order to keep the feedback loop as short as possible. And not only exhaust it, but go a little bit over in order to make sure that the Hazelcast members remain stable, even if the memory is full and even if clients continue to write to them, right? So what we can already see here, actually let me enable auto refresh. What we can already see here is that memory consumption is sort of going up, but it's going up too slowly. Remember, we have to get up to around, well, between 41 and 42 gigabytes of native memory that is to be exhausted, and we want to go over, actually. So, yeah, I think we're gonna hit this limit at some point, obviously, but at this pace, it's going to take a couple of minutes to do so, and that is too slow for us. And that gives us the next iteration of our Hazeltest load config. So let's do a short comparison between values, stage 1.1 and stage 1.2. So in value stage 1.2, we adjust load dimension 4, that is the number of clients, by simply scaling out horizontally. Rather than providing one Hazeltest instance, we provide 10. So correspondingly, we don't need to write 400,000 maps for each instance, but simply 40,000. That's simply a result of having 10x'd the number of replicas, right? So that's another way of reducing the total runtime for the test, which is always a good thing, because the shorter the test runs, the quicker we've got feedback, the quicker we get feedback on the fitness of the release candidate, right? So before we deploy that, let's check our Hazelcast cluster members. And this is something I've mentioned previously. There is a really, really serious configuration error in here, and yet the members are still stable. And they will continue to be stable until, there's really a lot of load on them, right? So this is pretty dangerous. Right. So let's deploy that file. Simply gonna switch out a 1 for a 2. And before I do that, yeah, we've reached 5 gigabytes, but it's already taken us like 2:39 p.m. to about 3 minutes. That's too slow, right? So, with that once again verified, let's deploy a new Hazeltest configuration. So 10 instances spawned, and these are all running, no surprises there. So what you're seeing here is the state cleaners kicking in, so they erase all state in the target Hazelcast cluster. And then after we've gone down to 0, you will see a stark increase in the amount of memory used shortly thereafter. And here we go. That is a very stark increase indeed. Very significant increase indeed, and we've already reached 14 gigabytes. So let's wait a little longer and check what our Hazelcast members look like. Yeah, OM killed. So that's no surprises there. That's how it should be. And we have thus successfully identified the very significant flaw in our stage 1 Hazelcast configuration. Yeah, metrics are all over the place now. So I'm gonna uninstall everything, and then we're going to install Hazelcast from scratch with the next configuration file. A little bit of video editing magic later, and we've got ourselves a clean slate. So let's try the same thing again, but this time we're going to use, obviously, the stage 2 file. Wait, Helm upgrade, there we are, and we want stage 2. So once again, this will give us 3 members plus a management center, and while this is booting, let's take a look at the differences between stage 1 and stage 2. So, stage 2 sees the JVM, the XMX and XMS values significantly decrease. That is, the heap is now a lot smaller. And if you do, like, the numbers, 16 plus 3.2 is 19.2 gigabytes. And that's a little bit smaller than our limit of, our container limit of 20 gigabytes. So let's see if this is sufficient, because a buffer of only about 800 megabytes really isn't a lot. But if it works, then that's great, because we've pretty much maximized the amount of net storage that we can actually use. So very little memory in this case, and thus very little money, would go to waste. But it has to be safe, obviously. So let's see if that's going to be the case, right? Okay, our Hazelcast cluster has been successfully deployed, and again, we're going to bring up Hazeltest. And this time, we're going to start with values stage 1, 2, once again, because that's the values file that made the previous iteration crash, right? So now we want to assert first and foremost that our stage 2 configuration is sufficiently reliable to handle the load that the previous iteration was not able to handle. So once again, we've got our 10 Hazeltest instances, and once again, we have to wait a little for data to come in. Perhaps I'll perform a little bit more video editing magic here, so you don't have to wait. Indeed, a little bit of video editing magic and a small correction of my camera later. We can see that the memory usage again significantly increases, which is what we expect. And what we also expect is that the members remain stable, right? Even when they are at maximum capacity, because we did significantly decrease the heap of those members, and we are now below the 20 gigabyte threshold with a little bit of buffer left. So let's see if that's actually the case, and let's also check how much time it takes for those 10 Hazeltest instances to completely fill up the memory. Remember that we want that time to be as small as possible in order to maximize the number of iterations we can do within one given unit of time. A short while later, and we have successfully exhausted our the memory capacity in our Hazelcast cluster. Let's check the time. Let's do a very simple measurement of how much time it actually took. That's 2:47 p.m. to 2:49. So it took 2 minutes, roughly. Yeah, a little bit less than 2 minutes to exhaust our 40 gigabytes of net storage. That's actually a little bit less than what I mentioned previously. And we can see here that the test is already ending. So the batch test loop is now in its delete phase and is about to end. And let's check our Hazelcast cluster members, and they are doing pretty fine. So as far as this particular load configuration is concerned, the rather small buffer of 800 megabytes seems to be sufficient. So that's good. And in the next step, yeah, test is done. Let's just check the logs. Yeah, finished map load test loop. So this is done. What? There was some error messages. Error encountered. Yes, obviously. Yeah, you will see these because obviously once you reach the memory capacity and you keep ingesting stuff, then eviction kick in, and this eviction will kick out all the values according to the eviction policy that has been configured, and therefore the read all batch won't actually obviously be able to read back all the elements that it has previously written, because some of these elements have already been evicted. So those Hazelcast members looking pretty good, and the Hazeltest load test being finished, let's uninstall Hazeltest and also get ourselves a completely fresh Hazelcast cluster, and then shift a gear higher by providing a, let's say, slightly more aggressive Hazeltest configuration, because we've just taken a measurement and it's taken 2 minutes to exhaust, that 40 GBs of memory. And that's a little bit too much for a smoke test. So that's significantly better than what it would have taken with the previous Hazeltest load configuration, but we're still not quite there, and I think we can still do a little bit better. Right, so let me uninstall Hazeltest. Uninstall Hazelcast. Everything's terminating, so let's pull up Hazelcast once again with the values stage 2 configuration, mind you. And while that's booting, let's take a look at what we're going to install next in terms of Hazeltest. So let's do a short comparison between values stage 1, 2 and values stage 2, 1. Alright, so we're still going to use 10 replicas, so no changes there, but we have increased the memory request and limit for our Hazeltest instances slightly, and that is because we now sort of deviate from our, presumed payload size estimation and go for slightly, in fact significantly, larger payloads. And we've also disabled fixed size payloads and instead enabled variable size payloads. So that's a change in load dimension 2. And because we write items that are larger, we can also decrease the number of entries that we need to write in order to, fully exhaust the memory of the target Hazelcast cluster. That is in order to shorten the test load time, the load test time yet further. So that's a decrease in load dimension 1. Okay, so this is all ready. Helm upgrade Hazeltest, and this time we install 2.1.yaml. Let's go. Yeah, this one has achieved readiness as well. That's good. So let's once again... Oh, yeah, that is very quick indeed, isn't it? So in the next tick, in the next, refresh of this dashboard, we should have already reached our roughly 40 gigabytes of memory. There we are. It's now reaching those aforementioned 41.6 gigabytes, presumably because the native memory, the default memory allocator that's used for the native memory, which is called the pool memory allocator, has to do a little bit of housekeeping work, that is, use more metadata in order to accommodate the fact that we now have, not fixed size payloads as we had previously, but variable size payloads. And the pooled memory allocator isn't actually that good dealing with variable size payloads, which was, by the way, the reason why the feature in Hazeltest was implemented in the first place, because I needed to do some verification for my Hazelcast, for my client's Hazelcast clusters, which are using the pooled memory allocator. So either way, we have successfully exhausted the full memory of our target Hazelcast cluster in a matter of 255 to 255.30. So 30 seconds to exhaust all the memory, and that's a lot better because with a smoke test running as quickly as it is still running, but we've reached maximum memory capacity in a mere 30 seconds, and now everything that's going over it is additional proof that the Hazelcast members are able to withstand that kind of load, even for some some extended period of time. But we could, of course, optimize the number of maps to write such that it stays up here for only 20 seconds or so and then stops the load test loop. So this will keep running for a bit, and let's check how our Hazelcast members are doing. And indeed, we're getting very, very close to that, that 20 gigabyte limit. So that buffer of 800 megabytes seems to be getting a bit tight now. It wouldn't take a lot more for those Hazelcast members to get, OOM killed. So let's see if we can exhibit an OOM killed using the values stage 2.2 Hazeltest values file. Back in the dashboard, and we can see that the load test was successfully finished, which is something, you'll also see in the logs, of course. Yeah, finished map load test loop. And our Hazelcast members are still there, so that's great. And just like last time, I'm gonna uninstall everything. Yep, uninstall this, uninstall Helm, uninstall this as well. Great, everything's terminating. So we're gonna recreate that cluster. We're still on stage 2, right? Right, the cluster is getting pulled up, and just like last time around, I'm gonna walk you through the difference between stage 2.1 and stage 2.2. Yeah, here we are. We have specified a new property, append client ID to map name. This is only a small detail, but it is a very significant detail, because what's going to happen is that right now we had, or in the previous 2 configurations for Hazeltest, that is, we had 10 replicas, and each replica used 30 maps. But the only thing that was appended to the map name was like the index of the go routine that writes on each map, right? So ht_load-0, for example, for the first go routine, and then of course, ht_load-n, and then ht_load-29 for the 30th. That's a difficult word for me to pronounce. Anyway, for the last go routine. So in other words, all the Hazeltest instances, all 10 Hazeltest instances, used the same map. If you specify append client ID to map name to be true, then what's going to happen is that each client, that is each Hazeltest instance, will have its runner's test loops append the client ID to the map name. So this is going to do is give us 30 into 10 maps. So we're going to end up with 300 rather than 30 maps. So that is a pretty significant increase along load dimension number 3, right? And everything else in this load configuration, as you can see, apart from this comment, which I deleted, is the same. So the load is exactly the same, except along load dimension 3, which we have increased. So with our Hazelcast cluster running, let's see if we can use those additional maps in order to, prove that the buffer of 800 megabytes is too small. Let's do that. And I'm actually pretty curious for this as well, because remember that we have enabled variable size payloads, right? And these are sort of a black box, because there is a significant element of randomness in here. Of course, the way it works is that you've got low boundary bytes and an upper boundary bytes, and within each iteration, the map actor, that is the map go routine, will pick a new random number, corresponding to those boundaries. So you can never really tell how large each payload is going to be due to that element of randomness, right? So the last time I did, previously when I ran a short, kind of practice for this live demo, the intended effect actually happened of sort of pushing the Hazelcast members over that memory limit and having them killed. And I'm very, very curious to know whether the same is going to happen this time. This, of course, would be amazing, because then we sort of have the silver platter of necessity for doing another iteration on our, Hazelcast release candidate, which would then, bring us to stage 3. So once again, let's go over here and check our dashboards, and we've already reached maximum memory capacity. And let's check the Hazelcast Management Center as well. I gotta log in again because it's a new instance, obviously. So right now we have 300 payload maps plus some, system internal. And let's check the dashboard. Actually, there's not, that much going on here. The relevant bit here is that we actually have 300 maps. So in terms of CPU load, yeah, this is still all right. But what we can see here, of course, is that native memory usage and committed native memory goes up very, very quickly. But this is something we can see, and we just saw here in the maps dashboard as well. So let's see if this little bit of additional load is actually able to push our Hazelcast members over the limit. Thus far, they are still stable. Let's see. Okay, short while later, we've reached 99%, and there it is. Woohoo! Okay, what was the issue? Yeah, it got OM killed. Okay, I was lucky in this run too. So that little bit of additional load was actually sufficient to pull them over, and it happens consistently now, in fact. Okay, point successfully made. We need to do, as it seems, another iteration on our release candidate. Let's head on onwards to stage 3. So, once again, uninstall Hazeltest, uninstall Hazelcast. And I'm going to walk you through the differences between stage 2 and stage 3 so you can actually see what we've changed. So we have increased the heap a little and decreased the native memory somewhat from 16 to 14 GBs. Why did I increase the heap? Because 3.2 gigabytes on a JVM, on a Hazelcast JVM, really isn't a lot. And it would be very easy to come up with a scenario or with a load pattern, let's say, in which these JVMs would get into significant trouble. All it takes really would be a little bit of on-replication traffic and or some queues and or some, some reliable topics or, traffic on any kind of data structure really that cannot be offloaded from the heap, i.e. that is stored on the heap itself. So, it's a pretty good idea to make that heap a little bit larger and in turn make the native memory size a little bit smaller. So now we have a buffer of 1.5 gigabytes. That is still not an awful lot. So you could probably come up with a load scenario in which even this buffer would be too small, and the members would run into an OOM error. But as we will see, this configuration is sufficient to handle load created by our stage 2.2 Hazeltest load config. Or will it? Let's see. Right, did I already? No, I didn't. So let's install that. No, that's Hazeltest. Yeah, values stage 3. Let's go. Okay, I should have first hit that button and then provide the explanation. But never mind, there's already video editing magic is always available at your disposal in order to, jump over little wait times. So let's see you in a couple of seconds. Right, a couple of seconds and a sip of coffee later, and our Hazelcast cluster is once again ready to go. So we're going to install the very same Hazeltest configuration once again, value stage 2.2.yaml. Let's go, and this, creates 10 instances. By the way, if you notice that some instances reach readiness later than others, that's due to the state cleaner being active. The state cleaner is a feature designed to, clean state, really. Quelle surprise. And if, instance number 1 gets a lock on the, map that is, that these Hazeltest instances, or their state cleaners rather, used to synchronize their state cleaning, then the Hazeltest instances that start afterwards will wait for that lock to be cleared. And that, that couple of seconds means that they will achieve readiness later on. But if you think that's annoying and if you don't need state cleaning, just disable the state cleaner. Anyway, now we've got our load. Let's check once again. Yeah, once again, that was really quick, right? So we're just gonna let this test run, and now the Hazelcast members should be, stable. They should not be OOM killed. So the total amount of memory that we now have to exhaust is obviously a little bit lower than previously, because the value stage 3 Hazelcast configuration only leaves 14 gigabytes of native memory on each member rather than the previous 16. So the point where we reached the 100% memory capacity as far as the net memory capacity is concerned was once again very, very quickly reached. Although this measurement in here is a very simple one indeed, and it's not very accurate due to the, scraping intervals in Prometheus being 30 seconds. So these, these timestamps here should be taken with a grain of salt. So let's once again take a look, and we're probably about halfway through the test now, and as you can see, we are comfortably question mark. Is it a comfortable buffer that we still have? Probably not. So if this were a configuration that we'd have to ship for production, I would suggest doing, more iterations and, making sure that we actually test for all the data structures that our Hazelcast cluster is going to have to work with in production. But at least as far as this load pattern is concerned, we're doing reasonably okay. So, with this kind of memory consumption, we're not going to run into any danger of being OOM killed anytime soon. So that's looking a lot better than the stage 2 configuration, doesn't it? So by now, yes, the load test is already over. We can see that we can check that using the set count and the get count and then the remove count, by the way. So this is perhaps something, interesting to watch. The set count means obviously that the batch 2's test loop is currently doing its ingest batch. And then once it's done that, it will switch to the read all batch. So here you'll be able to observe the get count going up. And then once that's done, which will be a really quick one, the remove count will go up, and correspondingly up here, the entry memory cost will significantly go down, as well as the map entries, obviously. Why will it do that? If there's, I mentioned previously, if you paid close attention, this might raise an eyebrow on your end now. Why is the entry memory cost going down all the way if there is an element of randomness in the delete quote unquote some batch, right? Because the delete some batch is only supposed to delete some of the elements. Well, that's because once the map load test, the map load test loop was finished, it does an evict on all the maps it has used. So if we had more than one run, that is, if the cycle of batches ingest, read, delete were repeated over and over again, you'd see this kind of zigzag pattern that you've seen previously in the slides, right? With, you know, ingest all and then read all and then delete some and then again ingest all. So this would kind of give you that totally wild zigzag pattern. That's not the case here, because in this case we only do one run in order to, again, keep the smoke test time as short as possible. So the total runtime of our test is roughly, again, this measurement is not very sort of precise, because let's actually check the logs. That's a lot more precise, right? So k-n Hazelcast platform logs Hazeltest, and let's take this one, and the log buffer isn't large enough, so unfortunately we can only see these log messages. Map test loop done. That is unfortunate. That is very unfortunate. So let's do the more inaccurate measurement of how long it's taken. So this was the start, right? 3:08 p.m. and here, roughly, the test concluded. So that's about pretty much not exactly 3 minutes and 15 seconds. So again, as mentioned previously, it's important to exhaust all the memory and then let it run for a little while to make sure that, you know, the Hazelcast members remain stable. Because remember, when we had the stage 2 configuration, the OM killed events didn't happen right here. Instead, they happened a couple of seconds in, right? So even in a smoke test, you'll want to let this run at least for, you know, 30 to 40 seconds. So this could be optimized a little further by reducing the number of map items to be written, because that would mean that, you know, there is less to write, and the load test would conclude further. So that is, you would have to, you know, decrease the along load dimension 1, and the setting is this one: num entries per map. Right. So I'm totally going off script here, but why not try to, you know, make the stage 3 members crash as well? Because we've just now, you know, concluded that stage 3 is sufficient to handle the load created as a result of applying, you know, Hazeltest in a configuration that specifies load according to this file. But we can always create more, and we can always, you know, pretty much make any kind of Hazelcast cluster member crash, no matter the configuration, by creating yet more load, right? So, you know, let's do a values stage 3.yaml before we play around with that. Let me uninstall both Hazelcast and Hazeltest. Now let's bring up a new cluster for a new Hazelcast cluster. Yep, this is the one, and go for it. That's great. So let's design our value stage 3.yaml, aka Doom configuration file. So there are so many possibilities of how we could increase the load. The simplest way to make stage 3 crash would be to to create load on a data structure that's stored on a heap, because remember that in stage 3 we only provided a buffer between, you know, this plus that, 20 gigabytes minus the sum of this, of 1.5 gigabytes. And that's not a lot. It's more than the previous configuration, but it's still not a lot. So we could simply enable the queue load runner and, you know, give it and tell it to create rather large payloads, and that, you know, our configuration would immediately go boom. But that's kind of like cheating, because today the focus is on the map load runner batch test loop combination, and so I don't want to use the queue load runner, right? So we're gonna do this with only the means offered by the map load runner and the batch test loop. So one way to create more load would obviously be to increase the number of replicas. That is, increase along load dimension 4 the number of clients. We can do that, but let's not. Instead, let's set the number of maps to 300, 10x that. Leave append client ID to map name to true. So this will give us 3,000 maps in total. Actually, let's make that 6,000, because why the hell not? And then I want large payloads. Let's up this to 100,000. Which would be 100 kilobytes, and the lower boundary should be 20 kilobytes. What that means is that we have to give those Hazeltest instances a lot more memory due to the way the Hazelcast client itself works when, you know, writing these payloads to the target Hazelcast cluster, because, you know, internally Hazeltest creates the payload, creates a dummy payload, and then uses pointers, obviously, wherever possible. But at some point, you're gonna have to, you know, write the actual payload to the target Hazelcast cluster rather than a pointer to the payload, right? And so at some point, you're gonna have to make a copy of that underlying payload. Hence, if we, and that's gonna happen on each of these map coroutines, right? So if we specify 600 map coroutines, which is quite a bit, and make the upper bound, make the payloads larger, then we're gonna have to specify more memory. I don't know how much exactly that's gonna be. We could just take 600 into 100,000 as a reference, but that's in bytes. So 6,000 into, that's 60 million bytes. What the hell is this in megabytes? That's 60 megabytes, but we've already reached that. And I know that 80 megabytes will be too little. Let's specify 200, capital M, and hope that it's sufficient. I don't think it will be sufficient, however. I think we need to, you know, provide more. So, yeah, I think that should do. So our Hazelcast cluster is up and running, so let's install that file, and gonna have to reference it locally because I didn't push it yet. So that's code Hazel. No, that's blog examples. What's the path? Hazeltest, and then how to Hazeltest map load runner. Then what? Using the batch test loop, Hazeltest. Now we got it. Okay, Hazeltest and values stage 3.yaml. Oh, whoops. Right. So let's see who gets OM killed first, Hazeltest or Hazelcast. Let's see how quickly the memory is getting exhausted. I would guess very quickly. Yep, looking good. We've got... need to refresh that. Oh, the cluster is already unresponsive. Whoops. So I don't think we're gonna see a lot here because... yeah. It's already broken. Okay, so, well, mission achieved. Let's check. Yeah, OM killed. Okay, well, I would have loved to see some results, actually, but that did not transpire because the members got killed so quickly that we didn't actually, see results. You know what? I'm going further astray here in terms of the script for this live demo, but the beautiful thing of, being on Kubernetes and the beautiful thing of Hazelcast itself, obviously, is that we can simply scale up. I'm gonna create a clean slate for us, and I'm also scaling down the management center because we're not going to use it for this particular test. So I'm gonna destroy all of those and then, just scale up to, I don't know, 7 members perhaps. The point here is that I want to see some results in terms of metrics on the cluster, and if the members crash that quickly, then I'm not going to be able to retrieve any kind of metric from them. So let's scale out our Hazelcast cluster to 7 members and see how well those 7 members are able to handle the load, given the stage 3 configuration for Hazeltest and given also the stage 3 configuration for Hazelcast itself. Okay, so once again a little bit of video editing magic later. All 7 Hazelcast members are up and running, and now it's time to scale our Hazeltest set of instances back up to 10. And let's see how these Hazelcast members will be able to handle the load. Come to think of it, I should have disabled the state cleaners for all of those instances to achieve readiness at the same time, because it always looks kind of weird when there's one that hasn't achieved readiness yet, but it's not an error, so it doesn't bother us too much. And I just hope that this time around the members will stay alive long enough to, expose some metrics to be scraped by Prometheus and then read by Grafana. Let's see. Okay, as you can see, once again our Hazelcast cluster members run into out-of-memory errors. So the stage 3 configuration, as it turns out, is no good if you really, throw a lot of load at those cluster members. Now, we could allow ourselves the luxury of coming up with a stage 4 configuration and then make sure that the stage 4 configuration is stable enough and then create yet more load, kill the stage 4 configuration members, and then come up with stage 5, and so on, until my own little server couldn't handle the load anymore, until we get bored with it and until our coffee machines run out. But in the interest of eventually coming to an end of this video, I'm just gonna leave it here because I think that the point was sufficiently driven home. That point being that it's always a good idea to, do a couple of iterations on the memory configuration for your release candidate as a kind of sanity check, just to make sure that the memory configuration is able to handle whatever load you think is appropriate to assert that basic level of fitness that you want to assert within a smoke test. And with that, let's head back to the slides. So, after having successfully established that it's probably a jolly great idea to run a couple of iterations on your memory configuration before shipping the resulting Hazelcast cluster to production, let's do a short summary and perform a short outlook of what's in store next for this channel. So we've seen that the combination of map load runner and batch test loop is a great tool for performing automated smoke testing on your release candidates that describe a Hazelcast cluster in some way. The generated load, again, and that's also something we've seen, is not necessarily very realistic. In fact, I would doubt it gets anywhere close to what your Hazelcast clusters face in production every day. But turns out the degree of realism is far less important during the early test stages than quick feedback, or vice versa. Quick feedback is a lot more important than the degree of realism of the generated load in early phases of testing. But it's in this very statement, or in this very idea, that the challenge lies, right? Because once the basic level of fitness has been established, that is, once you have successfully done all the sanity checks and once you have established that basic level of fitness, the release candidate must be exposed to load that is a little bit more similar to what your target Hazelcast clusters will actually face in production. If you come from software development, that idea is, taken from there, because it's the exact same thing here. Typically, if you work on a code base and you deploy, you do a git commit, git push, you go push it to somewhere, and then some CI/CD pipeline builds your artifact. Perhaps it's a trusty old Jenkins running there, and ideally you have implemented a lot of, unit level, component level, and integration level tests on the code base itself that your trusty old Jenkins, or whatever you use to run your CI/CD pipelines really, will run through. And before those tests don't pass, the CI/CD pipeline won't even publish, or won't even build, let alone publish, let alone deploy that compiled artifact, right? So that's the first line of defense, kind of. And once it's past that, typically you deploy it. But then once you've deployed it, you again need automated testing to assert the next highest level of fitness. And once again you've asserted that, and once your release candidate begins moving, through the stages towards production, the testing needs to become more and more such that the generated load, or the generated requests, are more and more akin to what your release candidate will eventually have to face in production. So the idea is simply to bring the proof that whatever it is you're building is able to handle production requests and production load prior to shipping the thing to production. And it's the exact same thing for a release candidate that describes a Hazelcast cluster, right? So as your release candidate for a Hazelcast cluster, for example, the Helm chart, moves through the stages, the degree of realism for the generated load becomes more and more important. Up until the load test, for example. A load test should be as realistic as possible. But at this kind of stage, you don't necessarily care about, the speed or the time within which you get that feedback. Sure, the time is still, if the time is short, then that's nice. That gives bonus points to test execution. But what you're really interested in at that point in testing is the realism of the load that the Hazelcast cluster is exposed to. And the combination of map load runner and batch test loop in Hazeltest is simply not a great fit for that. However, the combination of map load runner and boundary test loop is, at least it's a lot better, because it lets you model the production load more closely to satisfy that requirement for higher levels of realism. And that's exactly what we're going to do and what we're going to take a look at in the next video. So that's it for today, ladies and gentlemen. Thanks for watching. I'll see you next time, and until then, happy Hazelcast load testing.